Define glaciation. Define glaciation. This is the action of ice. Other people have come up with different definitions of what glaciation is. Let's have a look at what exactly glaciation is. We can say that glaciation is defined as the action of moving ice. We can also say it's the process when mountain peaks are accumulated by massive ice blocks. Also, it's the process of removal, transportation, and deposition of ice from one place to another, especially on highland to lowlands, that is formed when temperatures decreases under freezing point. Also, one can say it's the production of glacial phenomena. However, this description sounds devoid because it has still used the same word to define itself. Someone else can say it's the movement of ice from a central area of accumulation, like a mountain top, due to gravity. On the other hand, a glacier is a mass of ice, or it can be defined as a large accumulation of ice that is formed when temperature decreases below the freezing point, that is below 0 degrees Celsius, and it cools and solidifies, especially on highlands. That's what you call a glacier. So technically, a glacier is a mass of ice of limited width which moves outwards from a central area of accumulation.
Out, the ice will turn a bluish color. Glaciers have several components. The area where the snow falls is usually the part of a glacier with the highest elevation and is called the zone of accumulation. Further down the glacier,
so technically the process of ice formation is when there is accumulation of snow on the ground is below freezing point, that is 0 degrees Celsius. So there is that snow accumulation. Then beneath there will be the weight being exerted, leading to formation of a harder mass known as neve or firn. And they will appear like this as granular snow ice. You see, it appears like sugar granules. As more accumulation of snow continues, let's say it reaches up to 10, there will be even more compression, so that the hard mass becomes even harder. The air that was inside becomes squeezed out. So basically the air bubbles are no longer trapped. So the granular ice now turns into true ice, the real ice, which is blue. So you get to see this. Yeah, here's a close-up of the same. You see, it is bluish. It has a blue tint. Types of glaciers. We have continental glacier, Piedmont glacier, and Sac glacier. Let's start with continental glacier, also known as ice sheets. So we have the continental glacier, also known as ice sheet. This is a large and continuous mass of ice which covers a vast area of a lowland. Like this one is a lowland, technically a low-lying area. Then you can see that continental glaciers cover the surface, including depressions, hills, making the landscape to appear flat. Like here, it appears like literally it's flat. However, in some areas the hill peaks will be sticking out, and they protrude. So this is what we shall call the non-attack. So that is it. So these are the nunataks, those peaks. Also, it's worth noting that some areas like the mountain tops or plateaus have small but permanent ice sheets which cover limited areas of such places, the mountainous or alpine. For example, mountain top, mountain peaks. So we wanna see an example. Yeah, this are what we call ice peaks. Yeah. We have Piedmont. These are those that flow from steep valleys into a relatively flat land. Like this one is known as the elephant foot Piedmont glacier, which is found. You see how it looks? It looks like it fans out or spreads out. So you can see it fans out like butter, which has been poured into a pan. So beautiful, right? So here, beautiful, right? Yeah. The biggest glacier, which is a Piedmont, like technically to sit on the floor of a mountain, is the Malaspina Glacier. You can see, so beautiful, right? That is the Malaspina Glacier. Then, for the final type of glacier, that is the Sac Glacier. These are those that are glaciers that cover the corries, that is depressions along the mountain slopes. You see, yeah, those ones are the corries. When the ice sheet moves into the sea, a large mass of ice breaks off from the main ice sheet and floats. So this floating mass will be called an iceberg. That one. Just imagine how enormous it is. Like this, just the tip, 10%. So you can imagine 90% how it looks like. So amazing nature. So you can see, you find like it was once a large mass, then it breaks off. Then it enters the sea. Then it will be blown by wind and ocean currents. And once they enter the warm part of the ocean, they melt slowly and eventually disappear. Look at this iceberg that was seen in Canada. So yeah, it is. It will be blown by the ocean currents, then it will get to melt and finally disappear. On the other hand, a snow line is a boundary line beyond which there is permanent snow cover. Like here. Look at that. You can see where the flaky is. What are ice ages? These are intervals of time when large areas of the surface of the earth are covered with ice sheets. There are 4 of them. According to the Certificate Geography Form 3, written by the Oxford, we have 4 of them. Precambrian, that was 5 million years ago, and it's likely to have affected Central and Southern Africa, including Congo, Angola, and Zambia. You have the Ordovician, that is 488 million years ago. The areas affected in this era include much of North Africa, including the Sahara region, whereby the glacial rocks of this period have been discovered to the south of Aksum in Ethiopia, in Mali, Ahaga Mountains of Algeria. We also have the Carboniferous Permian that is believed to have occurred between 359 to 252 million years ago. And this age ice age affected Central and Southern Africa, including Congo, Zambia, and South Africa. The glacial drift, so that is basically the deposits. They occur now as tillite in several districts, for example, the Lualaba. Yeah. We also have the Pleistocene, which occurred 1.8 million years ago. I think this is the most recent. And it's referred to as the last ice age. It mainly occurred in the highlands of Ethiopia and East Africa, and also in the Atlas Mountains in East Africa, whereby the snow line was previously 2,000 meters, but it has now gone to 4.8 due to climate change, which led to recession of the snow line. So you can see there. I hope it's clear. And it's worth mentioning that the 4 ice ages occurred in Africa, and that different evidences, such as the glacial outcrops, you see, like this is a glacial outcrop. We also have compact and ancient boulder clay. We also have this, and being red, it means probably it has iron in it, like this boulder. Like these ones were found on the Great Lakes, that is holes. H for O for Lake Ontario, M for Lake Michigan, E for Lake Erie, then S for Lake Superior. Another evidence are the striations or the scratches left behind by moving ice on the harder and older rocks, like this one. We also have this one. That's how I show the okay. Like this one. Also this one. So I want to look at movement of ice. Remember that ice is not static. It is always in motion. So, and this is possible due to its plastic properties that enable it to slide and flow like a viscous fluid. Also, the movement can be through any of the 3 processes that I've written here, or a combination of the 3. So we have plastic flow, extrusion flow, and partial slip. Starting from plastic flowage, this happens within the ice mass, where such that great pressure is exerted on the layers at the bottom. And once that at the bottom, as well as on the sides and in the center, causing some ice particles to melt slightly. So once they have melted slightly, it means they'll change their position, hence moving downhill before they freeze again. So as the process is repeated continuously, we can see movement downslope. Though it can take several years, but we have seen that in recent times, the rate of ice motion has increased drastically by 20 times what it used to be a few years ago. We also have basal slip, and in this case, the glacier slides over the terrain on which it sits. What are we saying? That the weight of the ice causes the ice layer, which is in contact with the rock beneath, to melt slightly. So as it melts slightly, it means there will be a film of water which will act as a lubricant between the ice and the rock surface. So due to the force of gravity, the ice will be forced to slip and slide over the underlying rock. Remember, it has plastic properties, so it will always slide. We also have extrusion flow. This is whereby you find the movement affects ice sheets in lowland areas. So here there is no influence of gravity really. So the ice accumulates, and as it builds up to great thickness at the center, the weight which is resulting from that thickness compresses the layers of the ice beneath, forcing them to spread outward to where there is less pressure. Erosion. So in case you're asked the factors that influence the speed of a glacier, like the rate at which the ice moves, one, we have topography. And you can see the steeper the gradient, the more the movement due to the effective gravity. Unlike a place that is gentle. Amount of load, the more the load the glacier is carrying, it means there will be more resistance, hence reduced speed. We also have seasons. During the warm season, let's say during summer, there will be thawing, and this will promote melting, hence creating a lubricant that will allow the ice to slip over the underlying rocks. Unlike when it's winter time and there's a drop in temperature, which will mean the ice is freezing, so there is no movement. Then we have thickness and weight. The thicker it is and heavier the glacier is, the more the pressure it will exert, thus inducing slight melting to create a film of water, which will promote glacial motion. So we go to erosion, glacial erosion. We know erosion is the wearing away of materials. So glaciers erode the terrain through two main methods, that is abrasion and plucking. Plucking is also known as quarrying or grinding. So in this process of plucking or sapping or gouging, those are its names. So there you go. So it occurs when the ice at the base and on the sides of the glacier freezes onto the rocks, so that the rocks are pulled and carried away by the moving ice. And it usually occurs on well-jointed rocks like the limestone rocks or well-faulted rocks. So the ice melts slightly due to changes in temperature, then it will again freeze when there is a drop in temperature, or sometimes it can get to melt due to pressure, so that it gets into the cracks of the existing rocks. So once it has melted, it will enter into the rocks. Then when there is a temperature drop, the water will freeze within the cracks. So the freeze and thaw action, if it's repeated severally, so that there is an increase in volume of ice within the crack, the rock embedded in the ice will be under stress as the glacier moves forward, causing some part of the rock to break off. And once those rock particles are broken off, they'll be carried along by the moving ice, so they will form part of the moraine that will be used even as scoring materials in the process of abrasion. The other process is known as abrasion or grinding. This is where the rock frozen into the bottom of the ice will act like grit in sandpaper to wear away valley sides and the flow. So technically to say, in glacial abrasion, it's caused by rock debris embedded in the glacier, so at the base and on the sides, which act as tools for scratching and polishing the rock surfaces over which the glacier moves. So, and this happens as the materials are being dragged over the underlying rocks during ice movement. So you can see how it will cause, it will grind to cause the glacial striations. Okay, unlike this, you can see it's smooth, while on the rough surfaces here, these were caused by coaching. So we have other erosional processes, and these include pressure releasing. This is where the glacier melts, ice melts intermittently, easing its pressure, so the rock layers peel off. We also have bulldozing, where the water enters the cracks during the day and freezes into ice at night. It expands, and jagged angular pieces of break off and fall into the ice as moraine. So there you go. Yeah, that is it. I want to look at the factors influencing glacial erosion. We have velocity or speed. So a faster moving glacier will erode more because it has more energy to erode, especially by abrasion. And that will result into deep or can we say V-shaped valleys. Then we have thickness and weight of the ice. The thicker it is and the heavier the glacier is, it means that it will exert more pressure because of its weight. And therefore, the rock debris beneath will have more force, which will be effective in scrubbing the ground by abrasion. So there will be that polishing and grinding of the rocks. There's also the availability of rock debris. So the debris, as we know, they act as abrasion tools. So the more they are, the more they will enhance abrasion, and the more sharp they are, the more they will score an area, unlike the ones which are blunt. You can also look at the hardness. So the harder they are, the more the abrasion that will happen, unlike when they are smooth, so that they will not be doing scratching. You also look at the nature of the underlying rocks. So here you look at how jointed a rock is. So for those well jointed and faulted rocks, especially they are likely to be eroded more compared to homogeneous rocks that which have just one type of rock. We can also, and this is because the joints act as passage for water. They will allow water to enter in, the ice to melt, then enter the cracks, then it will freeze and thaw, and that will ensure placking. Unlike the ones which have just one type of rock, so there is no joints in such case to facilitate placking. Also, you can look at the softness or hardness of rocks. The softer the rock, the less effective abrasion will be. Unlike when you're using, okay, I'm saying this, abrasion is more effective on softer rocks because they're easily eroded, so they can be worn out easily, unlike for rocks that are harder. You can also look at the other things they're saying. The relative is to erosion of the glacier depends the following. There's also thermal conditions at the glacier base. So if there is melting, there is temperature increase, there will be melting, hence movement, and that will mean more erosion. Permeability and water pressure at the glacial base will also influence. Let's look at the glacial erosion features. For example, one may ask you, state 4 features produced by glacial erosion. So They could be on highlands or lowlands. On highlands, we have the Sac, Corrie, Arits, pyramidal peaks, also known as horns, Gardan. We also have glacial trough, hanging valley. We have the fjord, rock basin. Then on the lowlands, we have ice eroded plain. We have depression. We have Roche Mountain. Then we have the crack and tail. So let's look at them one by one in the next video. So a sac or a corrie is an amphitheater-like valley head formed at the head of a valley glacier by erosion. So someone can say it's a steep-sided rock basin which resembles an armchair. Some can say it's ball-shaped. How does it form? It is formed when snow accumulates in a shallow pre-existing depression on the mountainside or at the head of a valley. So that is to form a glacier. The ice will exert pressure on the cracks and the hollow beneath. As the ice moves, it plucks the rock in the hollow to allow more ice to collect in it. So plucking also contributes to the steepening of the sides and the back wall. A deep crevice known as a background may form between the back wall and the glacier in the depression. So you can see it here, you see. So, and it's arm-shaped. So if water gets to collect here, it will form what you call a sac or a corrie lake. A good example is this one, you see. So that is what happens, leading to formation of a sac or corrie. You can see that the plucked debris within the glacier will erode and deepen the flow of the depression through abrasion, resulting into a concave flow. See that one? That resembles the shape of an armchair. The edge of the depression on the downslope is called a lip here. Yeah, be called a lip. The glacier in the sac may melt, forming a lake which is called a turn. Yeah. So here is what happens. Like we have hidden Emerald and Gallery on Mount Kenya as turn lakes. So technically a turn or a corrie lake is a mountain lake or pond formed in the excavated by a glacier. The next feature is an arete, and someone may ask, what is an arete? This one. So arete is narrow, knife-edged steep ridge separating two sacs. It is formed when two sacs cut backwards on adjacent side of a mountain in a process known as headward recession. This backward cutting of the sac walls is through the process of plucking and invasion process. So that we have steep-sided neve-ridged ridges being formed. What are we saying? Nevation, in case you missed, it was under the formation of sacs, where we are told some snow which fell on the mountainside in small hollows may not melt at all during the summer. So over the years, it will build up. Then the lowest layers will be compacted and turned into ice. As this ice continues to build up, it starts to move down slope under the force of gravity, and so a glacier is born. So the process of nivation follows, whereby a hollow in a slope may be enlarged by freeze and thaw. So we had that neve, which was the initial ice that had been compacted. So it's enlarged by freeze and thaw due to withering and glacial erosion. So an avalanche brings down more snow and rock to add to the growing glacier. Eventually, this hollow becomes large enough that glacial erosion intensifies. So the debris in the ice may also cause grinding of the bed surface. So eventually, the hollow becomes a large ball shaped in the side of the mountain, with the head wall being withered by constant freezing and thawing due to the process of blacking as well as freeze and thaw. So the basin will become deeper if it continues to be eroded. So that is an arete. So here we're being told they are formed, they're also known as horns. Okay, we go to horns, also known as pyramidal peaks or gandamines. So this is a sharp and steep-sided peak surrounded by sacs. It is formed when sacs develop on all sides of a mountain. So due to the frost action, the block of rocks are broken down, resulting in the back walls of the sacs becoming steepened. The sacs then cut back simultaneously toward the peak. The aretes separating the sacs merge at the peak of the mountain. The merged aretes formed a jagged, sharp-pointed peak, which is pyramidal in shape. You can see like this, like what can be seen here. You can see they are sharp and steep-sided. Look at how piercing they can be. So steep, huh? On the other hand, we have also the glacial trough, which is a wide bottomed valley with steep sides. It can have a U-shaped profile, so that it can be known as a U-shaped glacial valley. You can see, yeah. So if water accumulates inside, it will form a lake. Look at how it is. It's very extensive. The hanging valleys. So once the glaciers deepen their valleys, then there's more than their smaller tributaries. The glacier will recede from the region, so that the valley glaciers remain above the main glacier to form what we call hanging valleys. So you can see there. And within the glacial trough, there are many features you can see, like the waterfall. You can have rock steps. We have alluvial fans once there's deposition happening. We have lateral moraine ridges. You can have reborn trough and finger lakes. So within that glacial trough. And we are told, okay, so there you can see. Like this is a hanging valley with water inside, so you can see it has formed a waterfall. So we can see that glacial troughs and the hanging valleys are possible because when the glacier moves down the valley, it starts to be fed by several tributary glaciers, so that there is increased erosive power, causing it to deepen, straighten, and widen its valley through the processes of abrasion, blacking, etc. So the ends of the spur that protrude into the valley are cut back by glacial erosion, forming truncated spurs. Since the main valley contains a larger glacier than the tributary valleys, the flow is eroded more deeply, making it to be at a much lower level than that of the tributary glacier. So after the ice has melted, the tributary valley is left hanging above the main valley. So the tributary valleys are what will be the hanging valleys technically. Yeah. So we also have a fjord. This is a long arm of the sea which is formed after a glaciated valley has been drowned by the sea. So this occurs when a glaciated highland coast is submerged into the sea. Let's say there has been an increase in water, so that it has been submerged. So glaciation through the process of blacking and abrasion will result in the widening and deepening of the lower parts of the pre-existing river valley, so that the interlocking spurs are cut back, making the glacial trough straight. So like here. So with time the glacier disappears after melting, leaving a steep sided U-shaped valley. So when the sea level rises, let's say there's been snow that has been melting, so the following will happen. The straightened and deep glacial valley will be flooded or be submerged by seawater to form a deep sea inlet, which is almost parallel to the sea, known as a fjord. So we have fjords are very common, especially in wildland. So a fjord is deeper inland but shallow on the seaward end. And we can also see the depth of water in the fjords may exceed 1 kilometer. So the great width and depth of the fjord is as a result of deepening of the former coastal valleys, such that the shallowness on the seaward end is due to deposition of the terminal moraine. So yeah, sometimes the terminal moraine may be too high to be covered by the seawater, so it will form what we call a scary. While the shallowness could also be as a result of a rock sill known as threshold. So yeah. So there you can see it. So that is it for fjords. So you can see the sea inlet there. So that's how fjords are formed in the grammatic. Then we have rock basins. They form in the glacial trough as a result of differential erosion, where two glaciers converge, so that erosion will be greater than where there is only one glacier. So a glacial hollow or rock basin will form at this point. During the post-glacial period, water may accumulate inside to form a lake basin or a ravine lake, also known as a finger lake. So you can see it there. Also, it's worth noting that a rock basin can also form in areas that have less resistant rocks. Yeah? So we can say we have soft rocks. So the glacier removes the soft materials to leave behind a shallow depression. The meltwater may later accumulate within the rock basin to form long and narrow glacial lakes or ponds known as ribbon or finger lakes. An example is Michelson, found on the trough of Mount Kenya, etc. So for the ice eroded plains, we know a plain is a relatively flat land. So in an extensive and almost level lowland, which was previously under ice sheet, we can see the ice can move across the land so that the moraine will cause separation and plucking, reducing the hills to low, smooth hills. So the place becomes relatively flat. So, and it will be characterized with shallow basins, low smoothed hills, you see, and the plains will later modify as the water from the melting ice is deposited on them to form till or boulder clay plains, which are commonly known as outwash plains. You see, these are outwash plains. So we have a rochemoteny, which is an elongated, rounded, asymmetrical bedrock knob with a gentle slope up its glacier side and steep to vertical side on the down glacial side. What we are saying is that this is a rock outcrop that has been eroded by abrasion and plucking, such that the side of the rock outcrop facing the upstream side, that is towards where the glacier is coming from, is polished by abrasion, resulting into a smooth, gentle slope, while the downstream end, where the ice is going, is affected by plucking, resulting in rugged and steep slope. And it could be up to a height of 100 meters and up to a kilometer in length, but most of them are much smaller. So that's a rochemoteny, like here. See? So there's abrasion, then plucking. So you can see if you're asked to describe a rochemoteny, you just need to talk about plucking as well as abrasion. So there you go. You can see the rest of the area has been polished, while the rest has been the downstream here. The downstream part has been plucked so that it is rugged and steep. Then we have a crag and tail. So this is a projection of resistant rock which protects a mass of softer rocks on the downstream side of the glacier. The soft rocks is what is known as the tail. Then we have the resistant rock, which could be an igneous volcanic plug, and the crag usually lies in the path of the oncoming ice. So the ice moves over and around the crag, but it's only able to slightly erode it because it's resistant. So the material that is being carried by the glacier is deposited on the leeward side, that is on the downstream side. So such deposits, together with weaker or softer rocks, are protected to form an elongated tail, and hence the term crag and tail. So you can see the side of the resistant rock is eroded, forming a crag. The opposite side, where the depression is called the tail.